All right, great. Thank you very much for the invitation to talk about my work. I'm presenting a very simple model that I've been working on with a couple other students, looking at how curriculum influences sharing of representations between tasks. I'm going to start off with what I think is the most classic example of illustration of the fact that the brain does use shared representations. If you look at these two sets of words, you'll notice that it is much easier to say the color that the word is written in the bottom group, where the semantic meaning is unrelated, than the top one. This is called the Stroop task, and it is one of the most robust findings in all of behavioral science. The classic explanation for this is that the semantically related tasks have shared representations which potentially interact or interfere with each other, whereas the semantically unrelated one has this independence that allows you to process the two tasks kind of side by side without any interference. And prior work has posited that there is a normative trade-off that underlines when the brain uses one solution or the other one that affects this relationship between multitasking capability, but also the sharing of knowledge or generalization, on the other hand, that you get from having these overlapping representations. I got interested in this phenomena from a bit more of a learning dynamics perspective, building on like a prior project that we did, where we tried to address one of the classic differences between human learning and neural network learning, which is the fact that when people learn several different tasks, they prefer to learn them one at a time and then move on to the new one and so forth, whereas a neural network would prefer treating them as one big task and having them in this interleaved fashion. What we found is that if we train this in a setting where there's no context signal, but the context needs to be inferred based on feedback in a two-path network, it is necessary to have a sufficiently long block length for your networks to learn this kind of flexible solution where each of the modules will specialize to one of the tasks, which we call the flexible regime. In this work, we characterize this kind of solution and the fact that you need this amount of time using this language of feedback loops, and do a parameter search which shows you this requirement of the long task blocks here. So if we kind of use these principles in the same approach, we can now study, apart from the pure normativity, what other factors influence when you have this shared pathway or these separate solutions that kind of play a big role. And we are using, in order to address this, just a very, very simple kind of TOR architecture here on the left-hand side, where we have a central path that is shared between the two tasks, and then these two individual paths, which only benefit one path by itself, connecting to these two output heads. And we can compare, if we train, which of these solutions the neural network is using, predominantly through the middle or predominantly over the sides. This is one sample trajectory where you can see the weights kind of growing along these different paths with these different magnitudes. If we now vary the block length across the whole spectrum, what we see is almost that the feedback loops result in these two discrete phases, where we have phase one with very little use of the separated pathway, and a phase two where the use is much more evenly split. And we can, in the case of linear neural networks, exactly solve these differential equations to give you the final solution at the end of learning that you get on the first path using differential time constants for the middle and the side pathway, and in the other case as several iterations with equal time constants where you go to the end of learning and train down to zero loss. This uses a reduction by a conserved quantity kind of method. My apologies that the equations are not showing properly here. So the prediction that we can make from all of this is that interleaving tasks for humans and animals might cause them to learn more shared representations, which could lead to behavioral correlates such as greater generalization or interference between the two. So thanks to the lab that I'm in, Christopher Summerfield's group in the UK, as well as my collaborators, and this is really still quite early work, so we're only now exploring bigger networks, possible behavioral experiments, and so forth. So please get in touch if this interests you. I'm also on the Discord in addition to email. Thank you very much.